I'm Wei. Today I'm going to introduce about xylanase. Xylanase is an enzyme that mainly degrades xylan backbone into small oligomer. What is xylan? Xylan is the second most abundant biopolymer after cellulose. It is a major hemicellulosic polysaccharide from plant cell. Xylan is a heteropolymer with backbone beta-1,4 cyanopropanosyl residue and branches of neutral or uronic monosaccharide and oligosaccharide. Xylanase can be used in many industries such as paper pulp, baking improving dot, extraction of coffee, palm oil, starch industry, and many more.
Hi, I'm Xin-Chi. I'm your tutor today talking about characteristics of xylanase. As we know that xylanase has many characteristics such as temperature, pH, beta-ion effects, substrate, specific, molecular weight, half-life, and enzyme kinetic. First of all, I'm going to talk about characteristic of xylanase, which is temperature and pH. For your information, enzyme is a type of catalase that lowers down the activation energy of the reaction. However, every enzyme has its own specific optimum temperature and pH in order for them to work under the most efficient way. So here, I would like to tell you that xylanase is a type of thermostable and pH stable enzyme. This is because xylanase has two catalytic sites based on the journal S. Gupta's title Solution Purification and Characterization of Xylanase from Staphylococcus in Biobleaching of Kraft Pulp. From this journal, we know that xylanase work under two different types of optimum pH and temperature. First, at 40 degrees Celsius, xylanase has a pH work under optimum pH at pH 6 to pH 10.5. The enzyme activity has as high as 70%. Secondly, xylanase that works optimally under 50 degrees Celsius has a pH range from 7.5 to 9.2 pH value. In this case, this enzyme activity is much higher than the first one, which is 90%. In enzyme technology, we know that every enzyme is has a very specific substrate binding site. In xylanase, the very specific substrate to it is xylan. Xylanase has 92% of enzyme activity on xylan based on journal S. Gupta Purification and Characterization of Xylanase on Staphylococcus in Bleaching of Kraft Pulp. However, xylanase also react with other substrates such as chitin, carboxymethylcellulose, and pectin. However, all these substrates has lower enzyme activity compared to xylan. Why? This is because the exposure of reactive group on the enzyme that can react with all these other substrates. But now, in your mind, you may have a question to ask. Since xylanase has different characteristics due to its structure, then is it every xylanase that obtained from different sources also have the same molecular weight? No. As you said, xylanase that extract from different sources will have different molecular weight. All these are based on our journal by R. Monisha. Title: Partial Purification and Characterization of Bacillus xylanase from soy source. From there, we know that xylanase that obtained from fungus will have 19 kilodalton. However, the xylanase from Bacillus species will have around 23 to 32 kilodalton molecular weight. Meanwhile, xylanase from Asparagus terrace will have around 22 kilodalton that is obtained from UL4209 strain. But why? Different sources of fungus and bacteria will produce different molecular weight of xylanase. This is because every bacteria and fungus will have different metabolic rate in their own cell. Thus, what they produce are different from one another. Here, I'm going to tell you about the meta-ion effect on xylanase. Meta-ions such as ferrum, 2+, nickel, lithium, copper is a type of stimulant to our enzyme xylanase. However, other meta-ions such as Fe3+, Ba2+, CO, and acetic anhydride can be act as a inhibitory to our enzyme xylanase. One of the examples such as acetic anhydride that inhibit our xylanase is due to the positive amino acid that is very critical for the enzyme activity that present on our enzyme. This is a factor that why acetic anhydride can act as an inhibitory factor to our xylanase. Somehow, beta-mercaptoethanol can stimulate xylanase because of the presence of cysteine residue at the active site of xylanase. Generally, we know that enzyme can be reused and recycled for many experiments. However, enzyme also has its limit because it will be denatured from time to time. So this we call it as half-life. Based on the same journal as before, we know that the enzyme that works, the xylanase enzyme that works at 50 degrees Celsius has 240 minutes half-life. However, enzyme that works under 55 degrees Celsius has lower half-life, which is 30 minutes. Xylanase has the lowest half-life when it works under 60 degrees Celsius.
Again, now I'm going to talk about Km and Vmax. As we all know, every enzyme has its own Km and Vmax towards the substrate. It can be calculated by using line variable plot. The larger the Vmax, the faster the enzyme can work and react with the substrate. The lower the Km, the higher the affinity of substrate can bind to the enzyme. So, according to S. Gupta, isolation, purification and characterization of xylanase from Staphylococcus species and bio-bleaching of kraft pulp, the Km of xylanase produced by Staphylococcus towards birchwood is 4 mg and the Vmax is 90 millimole per minute per mg. As for the Km towards oat spelt xylan is 7 mg per ml and Vmax is 55 millimole per minute per mg. However, different sources of xylanase have different Km and Vmax towards the same substrate, such as, according to Rajashri D, the xylanase produced from Heteros species have a Km of 0.9 mg per ml and Vmax is 3571 millimole per minute per mg towards birchwood.
Hello everyone, my name is Wen Hao and today I'm going to present to you the purification process of enzyme xylanase. The purification of xylanase basically consists of three main steps, which include the ammonium sulfate precipitation, ion exchange chromatography, and the gel filtration chromatography. Before I start about the purification process, I would like to talk about how enzyme xylanase is extracted. Enzyme xylanase can be found in various living microorganisms. According to a research article published by Gupta and his colleagues in 1999, which retrieved from the Journal of Applied Microbiology, a haloalkalophilic Staphylococcus species SG13 produced an alkylstable xylanase in wheat bran medium. In their research, the Staphylococcus species SG13 was isolated from an alkaline soil sample and was maintained on agar slabs. For xylanase production, the organism was cultivated in a medium at pH 8.0, which composed of 1% of weight per volume wheat bran. The medium was choked under 200 rpm, which stands for rotation per minute at 37 degrees Celsius. After 48 hours of incubation, the fermented broth was centrifuged and the cell-free supernatant was subjected to purification. In ammonium sulfate precipitation, the cell-free supernatant obtained from the extraction process previously will be treated with ammonium sulfate solution up to 80% saturation for enzyme purification by sorting out technique. The addition of ammonium sulfate into the protein suspension causes stronger electrostatic force between the protein molecules, which makes the protein more soluble and hence easier to be precipitated. The supernatant solution was left overnight at 4 degrees Celsius and the precipitate was then collected by centrifugation. Different relative centrifugal force were applied to different volume and concentration of protein solution. The precipitate was later dissolved in tris chloride buffer solution at pH 9.2 and balanced against the same buffer for 24 hours and then dissolved in the buffer again. The lysis was carried out using a cellulose tubing, which consists of a semi-permeable membrane. The main feature of the membrane is its porosity. The tiny pore size of the membrane allows small source ion to freely pass through the membrane, while larger protein cannot. Now we will proceed to the second step, which is the ion exchange chromatography. After the dialysis, the dialyzed protein will be subjected to an anion exchanger, which is the diethyl aminoethyl or DEAE cellulose column. DEAE is a positively charged resin used in ion exchange chromatography for enzyme purification. Resin DEAE locks the negatively charged enzyme amylase molecules into the matrix in the column. Equilibration and elution will be performed by washing with the same buffer solution to remove the unbound proteins. After that, the enzyme will be diluted with the continuous sodium chloride gradient, which varies accordingly to the concentration of the enzyme molecules. The action of the sodium chloride gradient is to weaken the ionic concentration of enzyme xylanase, which causes elution of the enzyme from the matrix. Finally, the fractions of enzyme xylanase will be collected. Now we proceed to the third step, which is the gel filtration chromatography. In this final step, the active fraction will be pooled and concentrated by using ultrafiltration. The highly active xylanase fraction will be then loaded onto a gel filtration column. For example, the Superlex G100 for further enzyme purification. Elution of the enzyme xylanase will be carried out by adding the same buffer solution. Finally, the purified crude enzyme xylanase extract collected will be free from the negatively charged particles.